Hey, welcome to the TEEP podcast, hosted by me, Gary Gildert. This is sponsored by the State Energy Conservation Office and Energy. We bring you the latest in industrial energy efficiency in 15 minutes or less. But we have a bonus interview this week with Dr. Alan Rossiter. He is retired executive director at Energy. In fact, he's my predecessor here at TEEP. He is a known leader in energy efficiency. Full disclosure, we've been friends for decades through AICHE, the South Texas section. And we're here this week to talk about pinch. So, Alan, tell me a little bit more about your background.
Very good, Gary. Good to talk to you again. So going back to the very beginning, I was born in Africa, what is now Zimbabwe, although back then it was Rhodesia. I went through high school there and then moved to England to the University of Cambridge, where I studied chemical engineering. After graduating from there, I went into industry. And by a weird quirk of having been to an 800-year-old institution, I was actually able to get my PhD while I was in industry. Cambridge has a system, or at least did back when I was there, or just after I left, that allowed you to get a PhD based on publications that you make outside the university. And I was able to get some things published while I was in industry, and that basically got me a PhD.
That almost sounds like the easy way, but all that writing is not that easy. I know.
Yeah, well, it was fun.
Okay, well, that's important. Fun.
Yeah, and I got paid while I was doing it, so yeah, I can't complain.
Oh, that's even better.
Yeah. So while I was at where I should back up, but when I left university, I went to ICI, Imperial Chemicals in England, and
a company that doesn't exist anymore.
Yeah, bits of it are in different parts of the world, of the world under different names, but yes. But while I was there, I got to know Bodo Linhoff. In fact, even while I was an intern, before I actually joined ICI, I got to meet or got to be in communication with Bodo Linhoff, and he is probably the best known figure in pinch analysis. His work, and some others, not just his, but his in particular, was very foundational to the development of the basic technology. And so I guess that's essentially how we get to be talking now.
Yeah, the father of pinch.
Maybe, yes.
Well, that does make you a disciple. You do realize that.
Yeah, I guess, yes.
Okay. So tell me a little bit about the history of pinch analysis, you like to call it.
So to get into this, I think you've really got to start by saying, what is the problem that pinch analysis is trying to solve? So if you think about it, most chemical plants involve heating and cooling, right? So I know you're a reaction engineering guy. I mean, a lot of reactors, you have a feed stream that goes in and it's relatively cold. And especially for an endothermic process, you have to heat it up, put it into the reactor so the reaction is going to go. Then you've got an effluent that's very hot, and you need to separate the constituents from the effluent stream, so you need to cool it down. And so you have a heating and cooling process going on. So the easy way to do this conceptually is to have some sort of heat source, which would typically be steam, or if it's a higher temperature, maybe a fired heater, providing heat onto your feed stream. And then you have to cool the effluent stream. So you just put an air cooler or a water cooler on it, and you can do your heating and cooling. But the reality is some of the heat you're putting into that feed stream may still be close to room temperature, depending on circumstances. And so you don't really need a 900-degree furnace to heat it up. And similarly, a lot of the temperature of the effluent stream is way above ambient temperature. So, why do we put all that heat out in a fin fan cooler or a water cooler? Why don't we instead recover some of the effluent heat and put it into the feed? Feed effluent heat exchanger. I think we've seen a few of those around in industry.
One or two.
And so that is the most fundamental form of heat integration. What pinch analysis tries to do is to say, okay, my process plant is not just a reactor with a feed effluent heat exchanger on it. There's generally a lot of other pieces of equipment, a lot of which require heating and cooling. So what happens if I try to do the best possible integration of not just the feed and the effluent, but of every other stream in the process as well?
Okay.
what is that going to look like? How much heat can I recover? How many heat exchangers am I going to require? Those are the sorts of questions then that pinch analysis is looking at doing, essentially optimizing the heat recovery process, the heat recovery within our chemical processes.
So you're going to be, so for our example here of a simple reactor, we all know that the reactor unit has distillation columns in it, separator
Mm-hmm.
columns, feed treatment of some sort.
Sure.
So the idea is to try to integrate the heating and cooling requirements for the whole unit.
Correct. So
Wow.
clearly it becomes more than just your feed effluent exchanger, but essentially a lot of places where I'm heating and cooling using process heat to the maximum extent that I can, and then only using those external, what we call utilities, just as the jargon you'll hear in pinch analysis terms, which can be either a hot
Okay.
utility, steam or furnace typically, or a cold utility, air, cooling water, refrigeration, depending on temperature level. But in between all of those, you've got as much process to process exchange as possible. And you could be, for all I know, integrating your distillation column reboiler with the effluent from the reactor. You don't have to just have a feed effluent reactor on the reactor. You can take some of that heat and put it into your distillation reboiler or whatever makes sense. And pinch analysis will tell you when you carry it out what the I'm reluctant to use the word optimum, what a good integration system, heat integration system should look like. If you think about this, there are essentially two steps in this, or two things
Okay.
we're thinking about. Number one is how much heat can I recover? What is the minimum heat I need to use? And similarly with cooling. And on the other side is how do I actually accomplish it? And so if you're looking at just what the how much is, then pinch analysis says you can find that out as a target, which is the term you'll hear a lot about in pinch analysis, before
Okay.
you know what the design looks like. You know you have a certain number of streams that are being heated up, a certain number that are being cooled down. You know what temperatures they have in and out. You know how much heat each of them consumes. The problem that you're really trying to solve is, given all of these streams being heated and cooled, what is the maximum amount of energy recovery or the minimum amount of heating and cooling, external heating and cooling, that you need to do?
Yeah, this sounds from the beginning like an accounting problem. Trying to figure out what heat needs to go in at what temperatures as well, I take it, in
Yes,
order to start
yes.
matching things up.
And it is indeed a sort of accounting problem. What goes in must come out essentially within, or actually that's not entirely true, but essentially there are heat balances there for your accounting. It's heat accounting, if you like, thermal accounting. The interesting thing is, there were really two main early steps in pinch analysis. And the first one is the concept of a target before design, which basically says if you've got all these streams being heated and cooled, and you want to put them all together and integrate them, what is the best you're likely to be able to do? The best you can do based on certain simplifying assumptions, but basically the best you're likely to be able to achieve in terms of heat going in by the heaters, heat removed in coolers. How much are those numbers going to be?
I take it it's not as simple as saying, okay, I need to heat 100 million BTUs. Well, surely I've got 100 million BTUs in hot streams that I can use. Is
Mhm.
it? It's more to it than that, I take it.
So pinch analysis, the historical, if you like, original pinch analysis is all about temperatures and heat loads. And so fundamental principle, what I call even more fundamental than anything else we say. Heat goes from
Okay.
high temperature levels to low temperature levels. That is
Okay.
fundamental.
That is
So going
fundamental.
so going back to your point, if if I've got what do we say, a million BTUs of heat, and I've got available, and I'm heating something up, and I need a million BTUs, can I therefore say, well, there's no net heat requirement from outside because these streams have got equal heat loads, just in opposite directions?
Yeah.
Well, under some circumstances that might be true, but it all depends on what the temperature levels are. Heat load and temperature level. Those are the two dimensions. And once you've understood that point, that, okay, heat has got to be at a higher temperature in the heat source than in the lower temperature, the heat sink, for them to match. If the heat sink, what starts as your stream needing heat input, if that is hotter than the temperature of the heat that is available to you, you can no longer use that stream to heat it, the hot stream to heat it. And you do this essentially across the whole of the plant. So you look at all of your heat sources, what are traditionally called hot streams in pinch analysis, whatever their actual temperature level is. And all of your heat sinks, the ones you want to heat up, and again, they can have a wide range of temperature levels. And you can essentially put them all together and rank them by temperature. So all loads at a particular temperature level are shown as essentially part of the same heat source or heat sink, whichever it is, one or the other. And
Okay.
then you can match them against each other and say, okay, what's actually going to match in terms of temperature level and heat availability or heat load.
So, is there a composite method of pulling this all together? Because I can imagine, even in a simple plant, you've got a half dozen or dozen different sources and sinks.
Yes, indeed. So yeah, the whole idea here is it is a combination of relatively simple mathematical computation, but also graphical representation. And so what you will see if you start looking at any sort of pinch document, there will be these composite curves, which are essentially the combined heating curves and the combined cooling curves that we were just talking about. And you also have what's called a grand composite curve, where you actually do some magic and turn them into a single curve. And these are used for different things within the scope of your pinch study. But the basic issue, and this really comes back to work by Ed Homan, I think it was his PhD thesis in, I believe, 1972, where he came up with this concept of targets before design. Even before you know what your heat exchanger network design is going to look like, you can come up with the target based on these curves that says, given the availability of heat and its temperature level and the requirement for heat and its temperature levels, you can essentially plot those curves and come up with a target for how much heat is going to be required net for net heating and cooling in the process once you've taken out the heat that you can recover by heat integration.
It's been a real pleasure as always. Thank you very much for putting up with me for this 15 minutes. Again, this is the TEEP podcast brought to you by SECO and UH Energy. I'm your host, Gary Gildert, and we'll see you in a week. Thanks.